All right, class, let's talk about something that's literally powering the device you're watching this on right now. Every single piece of electronics you own, from your phone to your gaming console, runs on stable DC power. But the juice from the wall? That's AC. In this explainer, we're going to dive deep into the fundamental circuit that bridges that gap, the diode rectifier.
So here's our game plan for today. First, we'll lay out the fundamental engineering problem we're trying to solve. Then, we'll look at two classic designs that try to tackle it. After that, and this is the important part, we'll create a performance scorecard so we can judge them like engineers, see how they stack up, and pinpoint the one huge problem that these simple circuits just can't solve by themselves.
Okay, let's just jump right in. Why do we even care about this stuff? Why is it so important?
Well, the grid delivers this nice, clean, alternating current, AC. But our electronics, they're picky. They need this perfectly flat, stable, direct current, DC. That's our goal, that ideal straight line. But what do we actually get from a simple rectifier? We get this bumpy, pulsating mess. It's full of what we call ripple, and getting rid of that ripple is the core challenge in designing any power supply.
So how do we make that first leap from AC to pulsating DC? Let's check out two foundational designs that you are going to see absolutely everywhere. First up, we've got the center-tapped rectifier. So during the positive half of the AC wave, boom, diode D1 turns on, and current flows along that orange path. Simple enough. Then when the wave flips negative, D2 takes over, following the green path. Now here's the clever part. Notice how it forces the current to flow the same way through our load? That's how we turn the negative part of the wave into a positive pulse. And here's the second solution, the one you'll encounter way more often. The full wave bridge. This one uses 4 diodes that work in pairs. On the positive cycle, D1 and D2 conduct together. On the negative cycle, D3 and D4 take their turn. And look at that output waveform. It's the same pulsating DC. The big advantage here is that we get to use a standard, much simpler transformer.
Okay, so we have two designs. They look a little different, but they get the same result. So which one is better? We can't just eyeball it and say, I like the look of that one. No, we're engineers. We need numbers. We need cold, hard data. And to get that data, we use what I like to call a performance scorecard. It's how we objectively grade our designs in 4 key areas: how much power they actually deliver, how efficient they are at doing it, the quality of that DC output, and how well they use the components we give them. Let's break it down. First up, the basics: output and efficiency. We calculate the useful DC power going to the load, of course, but the real star of the show is efficiency. This number answers the most important question of all. Of all the power we're pulling from the wall, how much is actually ending up as useful DC power? This is the ultimate metric for any power converter. Next, let's talk quality. And the metric you've really got to wrap your head around is the ripple factor, or RF. This number tells you exactly how much of that unwanted, leftover AC junk is still contaminating our DC output. A lower number is always what you're shooting for. This is our main grade for signal purity. And finally, utilization. How well are we using our parts? A really key metric here is the transformer utilization factor, or TUF. Think of it this way. A higher TUF means we're getting more DC power out for a given size of transformer. And what does that mean in the real world? It means a smaller, cheaper, and lighter product. That is a massive win for any designer. All right, we've built our scorecard. Now it's time to actually use it. We're going to run the numbers for the full wave rectifier and see exactly how well it does, or doesn't, perform. Now, don't let the calculus here intimidate you. You don't need to memorize these integrals. The key takeaway is that by using this math on the output waveform, we can find the precise values for the average DC voltage and the total RMS voltage. These two results are the foundation for every other number on our scorecard. So, what did we find? Well, first, the good news. We get a maximum theoretical efficiency of 81%. Honestly, for a simple little circuit like this, that's pretty darn good. We're successfully turning over 4/5 of the AC power from the wall into useful DC power. But here's the catch. The ripple factor is a staggering 48.2%. Let that sink in for a second. That means that almost half of the effective power in our output signal is just unwanted noise, this fluctuating garbage riding on top of our DC. That's a problem. And this right here really illustrates the core issue perfectly. You can see it in the inside box. An 81% efficiency is great. It looks fantastic on a spec sheet. But a 48.2% ripple makes the raw output completely unusable for pretty much any electronic device you can think of. This is the big problem we still have to solve. So when we put the two designs head to head, what do we see? A classic engineering trade-off. The bridge rectifier, most of the time, comes out on top. It uses a cheaper, more standard transformer, and it puts less voltage stress on the diodes. That makes it more cost-effective and versatile. But it's absolutely crucial to understand the pros and cons of each.
Okay, let's zoom out for a second, recap what we've accomplished, and figure out what our next mission is. Before we finish, I want you to ask, what is this ripple, really? Is it just random noise? Not at all. As this Fourier series analysis shows, it's actually a predictable sum of sine waves at different frequencies. And look, there's a huge, dominant component sitting at exactly twice the supply frequency. That's our target. To get pure DC, we have to design something that specifically kills that frequency. So let's recap the whole journey. We had a goal: turn AC into DC. We looked at two designs to do it, we analyzed them with our scorecard, and we found out they're about 81% efficient. That's a huge step. But we're left with this massive 48.2% ripple problem that makes our output basically useless for now. That is the next challenge.
Which brings us to our final critical question. We've done the heavy lifting of rectification, but the job's not finished. How do we design a circuit that can surgically target and eliminate that unwanted ripple, finally leaving us with the pure, stable DC our technology desperately needs? That, my friends, is the science of filtering, and it's where the real magic of power electronics truly begins.